Hello, and sorry about the delay. This is the next to last proper lecture in this course, and it's about differential or systems of differential equations. And here you will really appreciate, I hope, the linear algebra that you have learned so far. And let me just get started. So, the agenda is first order systems of linear differential equations. And the first thing I'm going to talk a bit about is how do they emerge or appear. And then I will talk about two systems, and one where the system matrix, and I'll define that in a while, have real eigenvalues, and one with complex eigenvalues. Then I'll talk about the structural theorem. Remember, it's a system of linear differential equations, and so you can consider it as a linear mapping in function space, and then you can use all the theory you have learned about linear systems. And this will allow us, say in a few cases at least, to solve inhomogeneous systems of equations. So this is the agenda. Now, what is a system of differential equations? There is an exercise today, and I'll just put it up here, or sketch it here. You have two tanks. Oh, draw another one. Two tanks of salt water, and they are connected. For one thing, there is an inflow here with velocity v of pure water. Then there is an outflow from the one tank here to the other tank. And then there is a, there's an outflow from the other tank. And due to conservation of volume and so forth, this will be equal to the volume of water flowing in here. So there's an outflow, but of salt water with velocity v here. But there will also be a backflow from, say this is tank 1 and this is tank 2, from the tank 2 to tank 1. So there's I should do it like this, and there's a flow this way. So the concentration of salt in this tank here depends, because of the backflow, on the concentration of salt in this tank. So they are interconnected and they are coupled. So whatever system that describes that should reflect this coupling. And I won't go into detail about how you actually get the system. I'll just write down the system because in exercise, it is exercise 6 today, there is a Mabel exercise where you go through all the details here, and so you'll learn about that. But the result is that you have that x1 is the salt concentration in tank 1. And the derivative of that with respect to time is equal to A, where A is a constant, times the salt concentration in tank 1, but plus B times the salt concentration in tank 2. So this is a differential equation that will govern the salt concentration in tank 1. Similarly, you have an equation for the salt concentration in tank 2, and it is given as well, it depends on the salt concentration in tank 1 because you have an inflow of the salty water in tank 1 into tank 2. But it also depends on the actual salt concentration in tank 2. So this is a system of equations, and A, B, C, and D are real constants. But you will have time to learn how this is actually done. Am I on? Yeah. Okay. This is one problem that you could try to solve. Another problem is that, or you could try to solve these or this system of differential equation completely, but often this is formulated as an initial value problem, and this means that we are given initial conditions and this could be that at time 0 we are given the value of the salt concentration in tank 1, but also the value of the salt concentration in K2. And now it turns out for a linear system, given these initial conditions, there is a solution. So the existence of the solution is secured, and it's unique. I'm not going into details about this, but there's an exercise, exercise 8, where you have to try to figure out this existence and uniqueness. It's quite fun, this one. You do all the work, and I just present it to you. But that's the best way to learn it. Now, The way we present this is often in matrix form. That is, we can rewrite this system of equations that we have. We have these two differential equations in matrix form. And I then introduce this column vector here of the derivatives. And then I write the right-hand side in the system of equation as the matrix vector product. A, B, C, D, and then times x1 of t, x2 of t. You see, if you multiply this column vector here onto this matrix, you get ax1 plus bx2. That is the first equation, and so forth. And now you can introduce x1, x2 as a vector. So this means a vector where the first coordinate is x1 prime, or the derivative of x1, and the second is x2, or the derivative of x2. And then this is again the column vector x1, x2, and then you have this matrix, which is A, B, C, D. And it is this matrix that is called the system matrix. Like this. And now we have to use linear algebra in order to solve this problem. Because remember that for such a matrix here, at least if it has, now we have a 2 by 2 system, and this 2 by 2 system, if it has two different eigenvalues, then you can factorize the matrix. So let me do that. So this is the left-hand side, and then I factorize the matrix in this way. V is a matrix where the columns are the eigenvectors corresponding to the eigenvalues. Lambda is a diagonal matrix where you have the eigenvalues in the diagonal, and then you should multiply by the inverse of V, and then times x of t. So you can do this. Now if I pre-multiply this equation here by the inverse of V, let me do that. Then I get and let me, this one here is the identity matrix, and this won't change the system. Now, this matrix here is a constant matrix. So when I multiply it on this derivative, I could also have written this in this way here. Or, sure, sorry, minus first. So that I first multiply x by this, and then I take the derivative. And this is because this is constant. So you can do this, and being the identity matrix, it won't change the system, and then you get in this way. And I could put a parenthesis here. So what you see here is that you have the same thing, take the derivative, it's equal to a diagonal matrix here, and this is important. And then you have the same set of variables here. In fact, this is just a shift of basis when you multiply by the inverse to v. So let me write here. If we take a new vector like this, then this is just a change of basis. Let me write it out. I could this is then this basis shift matrix, and then times x1 of t. But if I was given these vectors here, I could compute the x vector because I could multiply this by the matrix V, and then I get x1 of t, y1 of t is equal to V times y1 of like this. I could also write it in short form. The x vector is V times the y vector. So let me write this equation here in new variables. So I have y1 and then y2. This is the left-hand side, and on the right-hand side I have, let me just write it out. You remember that this diagonal matrix, you have lambda 1, 0, 0, lambda 2. And then you simply have y1 like this. Let me just compute this multiplication here, because I get then lambda 1, y1 of t, and 0 from the second term here, and then I get lambda 2, y. Sorry. Sorry.
Supposed to be x2 over there, or is it really y1 in the...
Ah, sorry. Thank you. And this is truly nice, because what you have obtained now is that the system is decoupled. You see, now the y1 only depends on, or the derivative of y1 only depends on y1, and the derivative of y2 only depends on y2. So let's see what we can do about this. You have that fact, I can write down, or even you can write down, the exact or the solution to this problem. You have a function whose derivative is equal to a constant times the function itself. So what should I write here for y1? Is there any? Sorry, sorry about that. Yeah. So I write, and then you have an arbitrary constant times that. And similarly for the other solution, okay, this is a general solution. So now we just have to write down because this is the solution we really want, x1 and x2. And if I go back, I see here that I should just multiply by this matrix here. C1. And in order to do so, I should know what is the V matrix. What should I write in the V matrix? Any? Yeah?
The eigenvectors.
The eigenvectors. So the first column here in the V matrix is the eigenvector corresponding to this eigenvalue. And the second column is the eigenvector corresponding to the second eigenvalue. And this should be multiplied by this one. And this means that I can just write the solution as C1. Remember when we have this matrix vector product, then we take the first entry here and multiply by the first column. So we get C1 E lambda 1 T, and then times V1. And then we get C2 E lambda 2T times V2. And then, and this belongs to R, or it could belong to C, depending on the system that you're looking at. But this is truly nice because you see here, you can write down the solution directly if you have the eigenvalues and the eigenvectors, and they're corresponding. So the first one, you have this exponential function with the first eigenvalue, and then the corresponding eigenvector, and then plus another arbitrary constant times the exponential of the other eigenvalue times t, and then the other eigenvector. So, and this works in general. So let if A is an a system matrix with n rows and n columns. And if this can be diagonalized, then you have that. You can write this the solution as C1e lambda 1t times the first or the corresponding eigenvector plus C2 lambda 2t, and then the second or the eigenvector corresponding to the second eigenvalue, and then finally you have Cn e lambda n times this eigenvector. And the constants C1, C2, Cn all belong to R or C, depending on the problem that you're looking at. Okay, so now you can solve systems of differential equations. You still have to interpret the solution and so forth, and you will do that in the exercises this afternoon. Let's take an example. I take the example where you have that, it should be x1. The derivative of x1 is equal to 10 x1t minus 12 x2t. And then you have this 8 x1t minus 6 x2 of t. And I'm going to pose two problems with this system. I want to find the complete solution. And B, I want to find the solution that fulfills x1 of 0 is equal to 1 and x2 of 0 equal to. So this is the solution that I want to find. So the first thing I do is that I write down the systems matrix. So this will be 10 minus 12 from the first equation. And then it'll be 8 minus 6 from the second equation. This I have done beforehand. These are the eigenvalues, and the corresponding eigenspaces are, the eigenspace corresponding to 4 is span and then equal to span like that. But now it's perfectly easy to write down the full solution And this is just one call to Maple. When you have defined this, then you call eigenvectors, and it will give you both the eigenvalues and the eigenvectors. So you have this. And so the complete solution in matrix form is x1 of t, x2 of t. This is your x vector, and it will be given. It will be given as c1. In fact, I have the solution given right here. So c1, and then e lambda 1 is 4, e to 4t, and then I'll have this eigenvector, and then c2, and then the second eigenvalue, which is -2, and then times the second eigenvector. This is the complete solution. Remember, when we choose an eigenvector, we could choose any eigenvector proportional to this eigenvector. But hey, this is multiplied by an arbitrary constant, so it's just a redefinition of this arbitrary constant. So whatever eigenvector you choose to write here, it will be adjusted by this one. Okay. Let me just write this system in the ordinary form. That is, I want to write it as two functions, x1 of t, and if I take just the first row here in this in this solution, I get c1 and then I get a 2 here, and then plus c2 like this, and then x2 of t I get c1 4 of t, and then plus c2 times e2 minus 2t. So this is a solution in the ordinary form, and remember, that c1 and c2 is now chosen to be real, because what we want to do now is that we want to try to solve the second problem here. So we want to find the solution that satisfy these initial conditions, that x1 is initially is 1 and x2 is 0. So let us just put this into the equation. I get x1 of 0. I put t equal to 0, so I get e of 0, that is 1. I get 2c1 and then plus c2, because here I get e of 0 as well, the exponential function of 0, which is 1, so it's c2, and this should be equal to 1. x2 of 0 is c1 plus c2 is equal to 0. Now, if I do it the way you have, that you now master, I write down the augmented matrix 2, 1, 1, 1, 1, 0. And then if I first subtract this from the first equation, I get 1, 0, 1, 1, 1, 0. And then I subtract the first from the second equation. I get trap t equal to 1, 0, 1. And then I get a 0 here, I get a 1 here, and subtracting I get -1 here. So I can read the solution as C1 is 1 and C2 is -1. And this will give the solution I have 1, 2, and then minus, and then I get e to 4t minus e. And let me just try to show you this, because what you see here, if you put t equal to 0, you get 2 minus 1. So x1 will get you go through this equation here, and then it will, and also this one, it will be 1 minus 1 at 0, so it goes through this one. When t is growing, then the last terms here becomes of lesser and lesser importance, because they tend to 0 as t goes to infinity. And the solution will be governed by the first term. And you see, as they go to infinity, and they will go really fast, and like this, something like this. This will tend to be double as large as this one as you move towards infinity. Similarly, if t goes to minus infinity, then these terms here will go to 0, and these are negative, these terms, and they will govern the equation or the solution, so they will go something like this. And here they have the same coefficient, so they will go asymptotically towards each other, but they will never meet. This is how the solution looks. And let's take a break until 11, and then I'll show you this in Maple, hopefully. Yeah.
Yeah, just a question.